So we can look at a graph and pick out a couple more features of it. One is the concavity of it. Concave down means just roughly that it opens downward or it dumps water. Concave up is where it holds water. Now a graph can do both concave up and concave down. And let me show you an example of that down here. Whoops, not too far. All right, where we've got concave down, dumping water, concave up, holding water. Okay, so with that information, we can say, well, when does it start holding water or dumping water? And that's where, again, we're going to look at the x-axis. So this goes down to negative infinity, but when we give an interval, we go from left to right. So we start at negative infinity, that's where our graph is starting to go downward, all the way over to positive infinity. That's where it's concave down. This one, concave up, kind of the same idea. All the way over here to negative infinity, there's going to be a point way up here somewhere, right, that my graph is going to keep on going to. And then, again, way out here to positive infinity, there's going to be a point on the graph that matches up to that as well. So it's always holding water, so it's always concave up. So from negative infinity to positive infinity, it's concave up. All right, now let's take a look over to this one. Now this one we're going to have to estimate a little bit, because it looks like from negative infinity, it's going down here, it's dumping water until we get to about halfway point here, and then it starts holding water again, or it's concave down and concave up. So if I just estimate it, you know, somewhere right around here is where it changes in concavity. And you're going to take a calculus class and they'll tell you exactly how to find that point. We're just going to kind of eyeball it right now. So this one is concave down on the interval from negative infinity all the way over to about -1. Again, it's kind of rough estimate. It might be a little less or a little more than -1, because it's actually negative like maybe 3/4, somewhere in through there. All right, and then it goes upward or holds water, concave up, from about -1 all the way over to positive infinity. And again, you're basing it off of the x-axis here. Okay. Let me go back to our graph over here. Notice this has a high point, if you will, and it's the highest point on the entire graph right here at this point, 0, 3. Call that an absolute maximum point. It's the highest point on the entire graph. We have an absolute minimum point here at 1, 0. It's the lowest point on the entire graph, because the graph's going to keep on going upward. Now this one, if I take a look at it, it looks like it has a high point here, but actually it's not the highest point on the entire graph because this keeps on going up. But it is a pretty high point. So what we're going to do is we're going to call this a local maximum, or instead of a local, you may see the word relative. And it means the same thing. Local relative maximum means it is a high point, but it's not the highest point on the entire graph. And then down here, that is a low point, but it's not the lowest point on the graph because, again, this graph is going to keep on going downward. So we call this a local minimum. Or again, you can call it a relative minimum. This doesn't have an absolute maximum because this just keeps on shooting up to infinity. And it doesn't have an absolute minimum because it keeps on going down to negative infinity. So you don't have an absolute max or min, but you do have local maxes or mins. And it's possible to have more than one local maximum or more than one local minimum in a graph.